Okay, hello everyone. Welcome to the second edition of the Basics of Quantum Gravity lecture series. So this is an initiative from the Young Researchers team of the International Society for Quantum Gravity. And the main idea is to provide young researchers with some tools, so this repository of lectures on different approaches to quantum gravity. So today we have Daniel Grumiller. He's um he's a professor in the Technical University in Vienna, and he's mainly known for his many contributions to 2D dilaton gravity and also to a related topic now that it's what he's going to talk to us about, that is Carrollian physics and holography. So we're very happy to have him. Uh, for some remarks is that we would prefer Daniel is happy to take questions during the lecture, but please it would be more convenient if you write the question in the chat so that I can moderate it, and I will let Daniel know that you wrote a question, and then we can either read the question in the chat or you can unmute and then ask the question. Okay. So thank you, Daniel, and you're welcome to start.
Okay, yeah, thank you very much. So I'll be giving a lecture series of 3 lectures on Carrollian physics and holography. And the first one will be on Carrollian symmetries and the Carroll conformal algebra. So here's an outline of the 3 lectures. Today, as I just said, Carrollian symmetries and Carroll conformal algebra. The next lecture later this week will be on flat space asymptotic symmetries and the BMS algebra. And the last lecture, which will take place next week, will be on aspects on the asymptotically flat space Carrollian CFT correspondence in 3 bulk dimensions and 2 boundary dimensions. Okay, so let's get started with today's lecture. I just had a meeting at the TU yesterday where we talked about the use of AI in lectures, and in particular the usage of students. And this has increased dramatically. So in particular, doing exercises. There's an echo. Yeah, so when doing exercises, the usage of AI has, gone from like 10% of the students used it to more than 80% of the students use it. So I decided it's maybe proper in these times to start with what ChatGPT would have to say about why should I care about Carroll symmetries. So everything on that slide is just a consequence of this prompt here to ChatGPT, to the free version. Why should I care about Carroll symmetries? And part of it is not so bad, actually, but I'll also point out some things that are a bit maybe unclear or confusing. So the main answer that ChatGPT gives is you should care about Carroll symmetries because they expose a deep and otherwise hidden corner of relativistic physics that becomes increasingly relevant across quantum gravity, field theory, and modern geometric approaches to space-time. Now, that's vague enough to be correct, but it goes on in more detail. So the first statement it makes is Carroll symmetry is a fundamental relativistic limit, not a curiosity. Carroll symmetry arises from the ultra-relativistic limit of special relativity, speed of light to 0, just as Galilean symmetry arises from the non-relativistic limit c to infinity. That's all correct. This matters because it completes the logical landscape of relativistic limits. That's also correct. It reveals that time dominates space, just as Galilean physics reveals space dominates time. That's a bit weird, but it's not wrong. Many physical systems and boundary theories naturally sit in this limit, even if the bulk theory does not. Okay, there's some truth to it. In short, Carroll symmetry is not exotic, it's complementary. Well, if it was just this fact, you would still consider it exotic because it's really the opposite limit of the limit that we care about in everyday life. And it's not so easy to envisage a scenario in physics where speed of light going to 0 matters. But there's more. So the second statement is actually, I think, the best one. It is central to flat space holography and asymptotic gravity. Carroll symmetries appear naturally at null infinity in asymptotically flat spacetimes. That's correct. The BMS group by Bondi, van der Burg, Metzner, and Sachs can be interpreted as a Carrollian conformal symmetry. That's also correct. I mean, more precisely, the BMS group, as I'll show today, is isomorphic to the Carroll conformal algebra or Carroll conformal group in one lower dimension. Carrollian geometry provides the correct intrinsic geometry of null hypersurfaces. That's also correct. And this is essential for understanding gravitational memory, soft graviton theorems, and the infrared structure in gravity. That's somewhat correct. So if you care about holography beyond ADS, infrared problems in gravity, scattering in flat spacetime, Carroll symmetry is not optional. I mean, that's a bit of a strong statement. It's not incorrect, but yeah. Then there's more. It provides the correct language for null dynamics. Many physically important systems live on or near null surfaces, event horizons, black hole membranes, light-like defects, shock waves. That's correct. On such surfaces, ordinary Lorentzian geometry degenerates, but Carrollian geometry remains well-defined. That's also correct. And the Carroll symmetries control the allowed dynamics, conservation laws, and straight tensors. That's also correct. So this gives Carroll symmetry operational relevance, not just algebraic interest. I would agree with that. The next one is a bit weird here. I don't fully understand what ChatGPT means. So it reshapes intuition about dynamics and causality. That's a bit a vague statement. In Carroll invariant theories, no signal propagates spatially. I mean, the light cone collapses. So unless you propagate outside the Carroll light cone, there's no propagation. All dynamics is ultra-local. Well, with some caveats, this is somewhat true. Time evolution exists without spatial motion. I mean, that's true, but it's also true in Galilean or relativistic mechanics. So this is useful because it isolates causal structure from kinematics. I'm not sure what is meant by that. It provides solvable limits of otherwise intractable field theories. Maybe. It clarifies what parts of relativistic dynamics generally rely on finite signal speed. I'm not really sure what that means. And these insights feed back into effective field theory and quantum gravity. Well, effective field theory, maybe, maybe not. Quantum gravity, as I will argue, yes, there's some relevance of these Carroll symmetries. Then the next point is it connects disparate research programs under a single framework. Carroll symmetry now appears in flat space holography. That's absolutely true. Soft theorems in celestial CFT. Well, it's somewhat true. There's a relation between celestial CFT and Carrollian amplitudes. Tensionless strings. That's absolutely correct. Null fluids and hydrodynamics. Yes, in a certain limit. And condensed matter systems with ultra-local dynamics. That's also correct. So what this tells you is that Carroll symmetry is a structural symmetry, not a model-dependent accident. I think I agree with that statement. And the last point is it's a diagnostic tool for limits, boundaries, and degeneracies. Practically speaking, Carroll symmetry organizes consistent boundary conditions in gravity, classifies allowed actions on null manifolds, and helps identify which degrees of freedom survive extreme limits. This is all more or less correct. And in that sense, it functions like conformal symmetry or gauge symmetry, a constraint that reduces ambiguity. That's absolutely correct, and I guess one of the main points. So whenever we have symmetries in physics, and in this case, it's an infinite amount of symmetry, that puts a large number of constraints on possible dynamics, even on kinematics, on scattering amplitudes, on thermal partition functions, etc. So it's useful to exploit these symmetries as much as we can and derive as many constraints as possible on physical observables just from the symmetries. So the bottom line that ChatGPT gives is you should care about Carroll symmetries because they complete our understanding of relativistic limits, govern the physics of null surfaces and flat space holography, provide the correct symmetry language where Lorentz symmetry fails. So that's the only point. I'm not sure what it means. The other I agree with. And unify several active research directions under single geometric and algebraic structure. Ignoring Carroll symmetry today is increasingly analogous to ignoring conformal symmetry in the 1990s, possible, but strategically unwise if you care about where the field is going. So I tend to agree with that statement, but of course not everybody has to work on Carroll physics. But it's true that the amount of papers that have Carroll in the title has increased exponentially over the past 3 years or so. So there's certainly a sense in which the community agrees to some extent with this statement. Okay, so this was the ChatGPT version of my talk in a sense. And now I fill in some of the details and make some of the statements a bit sharper and give it more content. All right. So here is a summary that Arjun provided 3 years ago. It's a summary of the previous slide in a sense. So what are possible application of Carrollian physics. I'll be focused on this orange rectangle here, flat holography. But as you see from this slide, there are numerous other instances where Carrollian symmetries have appeared. So from condensed matter physics, in the physics of flat bands, fractons, and others, in scaling limit of string theory, in particular tensionless strings, but also in the context of black holes, because, whenever you have null hypersurfaces, you have Carrollian symmetries, and black hole event horizons always are null hypersurfaces. So there are lots of possible applications of Carroll symmetries. Not all of them are sort of equally useful. So not all of them Carroll symmetries are of equal prominence. But in flat space holography, I think you just cannot avoid them because they are equivalent to the BMS symmetries, and they seem to be of big relevance for understanding asymptotically flat spacetimes. Okay, so let me finally start by defining what Carroll symmetries are. They are spacetime symmetries, and they indeed complete the known ones, so the Aristotelian, Galilean, and Lorentzian, by making space absolute but time relative. So it's the converse of the Galilean limit where space is relative and time is absolute. And it's a scaling limit of the Lorentzian case where both space and time are relative. And understood as a limit of the speed of light, it's again the opposite limit of the Galilean one, so the speed of light tends to 0. So whereas in the Galilean case, the light cone opens up, in the Carrollian case, the Lorentzian light cone collapses, and that's why if you propagate within the light cone, you can just propagate in time. And this is what Lévy-Leblanc inspired to give these symmetries the name Carrollian. Well, he was inspired by Lewis Carroll's book Through the Looking Glass, where there's the scene between Alice and the Red Queen, where Alice complains that she can't move even though she's running so fast, and the Queen replies, "Now here you see it takes all the running you can do to keep in the same place." So the limiting definition of a Carroll spacetime is a C to 0 limit of a Lorentzian spacetime. And that was discovered in the mid-60s independently by Lévy-Leblanc and Sen-Gupta. Now, while it is useful to have this limiting definition, it's also often useful to have an intrinsic definition. So you don't always want to approach Carrollian spacetimes or Carrollian symmetries as a singular limit of Lorentzian ones, because first of all, taking singular limits can be a bit awkward. You don't always necessarily know how to scale your observables with powers of C. And since C goes to 0, it's quite important how you rescale them before you take the limit. And if you don't know already what you want to obtain in the scaling limit, so if a corresponding observable is supposed to go to 0, to a finite value, or to infinity, then you may not know what is the right power of C to attach to this observable. And then you have to guess, and whenever you guess, there are chances you guess wrong. So for these reasons, it's useful to have an intrinsic definition of Carrollian symmetries, of Carrollian spacetimes, that doesn't rely on some parent Lorentzian construction. And the intrinsic definition for Carrollian spacetime is very simple. So you have a metric where you allow yourself for a degenerate signature. So you have, instead of minus plus 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 plus, you have 0 plus 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 plus. And in addition, you have a vector field that lives in the kernel of this metric. So the simplest example is flat Carroll spacetime. If you want, you can view this as a C to 0 limit of Minkowski, but let's just consider spacetime on its own. So ds squared is g mu dx mu dx nu. So this is 0 times dt squared plus a Kronecker delta ij times the spatial part, dxi dxj. So clearly, this metric is degenerate. It doesn't have an inverse. And there's a vector field that lives in the kernel. So the vector field in this case is just dt. And indeed, this vector field is orthogonal to the Carroll metric. So g mu v nu is 0. And you can convince yourself that this metric and this vector field, they're invariant under Carroll boosts, and Carroll boosts only act on time. So again, that's the opposite of the Galilean limit, where Galilean boost would only act on spatial coordinates. So xi gets transformed by some velocity times time. In the Carroll case, it's the opposite. So xi goes to xi. It's completely inert under Carroll boosts, but the time goes to time plus some boost parameters bi times xi. So this is what I meant when I said that in the Carrollian case, space is absolute, but time is relative. Okay. Now, let's consider now the why question. So why should we care about Carroll symmetries? And to answer this, let's solve the Carroll conformal killing equations. Probably many of you have done this in the Lorentzian case or from Minkowski space when you first were introduced to conformal field theories. So let's do this now here. We solve the Carroll conformal killing equations. So the liberation of some vector field acting on the Carroll metric is supposed to be proportional to the Carroll metric, and I call this proportionality constant 2 times lambda. 2 because, well, this is a symmetric 2 tensor. And at the same time, the same vector field, when it Lie transports the Carroll vector field, this should give minus lambda times v mu, minus 1 times lambda because this is now a vector field with one upper index. And I claim that these equations here have infinitely many solutions. So that's a big difference to the Lorentzian case. When you solve these equations here, so in the Lorentzian case, you only have the first equation and the metric is just the Minkowski metric. You find a finite number of conformal killing vectors depending on the dimension. I mean, it scales quadratically with the dimension, but you get, for instance, 15 in 4 spacetime dimensions. But here it turns out that even in a dimension as low as, say, 2 dimensions, you find an infinite set of Carroll conformal killing vectors that solve these equations. And they are given by this expression here. So you have one arbitrary function, t of xi, dt, and then you have some functions yi of xj that are constrained in the way that I explain in a minute. And they also appear here. So you have here a certain number of Carroll conformal killing vectors. The yi only generate finitely many, but the t is an arbitrary function, so you get infinitely many of them. So let me now prove this statement. And well, I consider the flat Carroll background here. So the Carroll metric is just the Kronecker ij, the spatial part, and the Carroll vector field t. If we solve the t component of that equation, this is just the commutator of xi with v, and that has to be minus lambda vt. And if you evaluate this, you just get minus dt xi t. So this just gives an equation for lambda. So this lambda is not arbitrary. It has to be given by dt xi t. Okay. The second equation, this is the spatial component of this equation here. Well, that just tells you that vi has to commute with xi, and that amounts to saying that dt xi has to vanish. So the xi i's have to have vanishing time derivative. So that's why these functions yi here only depend on xj and not on t. Okay, now let's move to the metric equations. The tt component tells you, well, nothing. It's automatically fulfilled because gt mu is equal to 0 for all mu. So that's a crucial difference, of course, to the Lorentzian case where the tt, gtt would be non-zero, of course. Now the mixed components, several terms vanish because, again, gt mu is 0, so only the last term contributes. And that just tells you that dt xj is equal to 0, but we knew this already. So this doesn't give any new information. So there's only one final equation. And, you know, if you are familiar with conformal field theories, you will recognize this just as the conformal killing vector equation in a Euclidean setup, so in one lower dimension. So this applies only to spatial indices here. And one of the consequences is that dt lambda has to be 0. And the other consequence is that the xi I, the spatial part of this Carroll conformal killing vectors, they have to be spatial conformal killing vectors. So that's why you only have finitely many of them. But the xi t is unconstrained except for these two equations. So since dt lambda has to be 0 and lambda has to be dt xi t, well, the general solution of this that you get some integration function t of xj plus t times lambda. And those lambdas are further constrained by this equation, and they have to be given by basically di yi up to some dimension dependent factor. So that means because of this integration function, we get a whole function's worth of Carroll conformal killing vectors. And that's the origin why you have infinitely many of them. Okay, so these Factor T has a name. It's called supertranslations. So T of xj dt generates xi dependent time translations. They're called supertranslations not because of anything with supersymmetry. It's a different super. It just means you have infinitely many of them. And translation just because these vector fields mutually commute with each other. If you take one function T of xj dt and another function T of xj dt, they commute no matter what these functions are. The best known special cases are when this function is constant, then this generates just time translation. So this is the Hamiltonian. When it's linear, this generates Carroll boosts, bi is xi dt. And when it's quadratic in the form xi, then this is a special generator that generates temporal special conformal transformations. So k is xi dt. So those generators you would be familiar with. Well, not exactly in this form because boosts have an additional term in the Lorentzian case, but at least the existence of these generators you should be familiar with from standard Lorentzian CFTs. But there's of course more. You can have arbitrary polynomials, or even if you allow them non-polynomial functions as generators of supertranslations. Okay, and the remaining part, this is well known. So this generates spatial translations, rotations, dilatations, and the spatial special conformal transformations. So these are all generators that you know already from standard conformal field theories. So in other words, the Carroll conformal algebra in D spacetime dimensions, abbreviated as CCAD, consists of this infinite tower of supertranslations and well-known generators that I denote in the standard way. So the spatial translations as pi, the rotations as jij, the dilatations as d, and the spatial special conformal transformations as ki. Okay. So this is the Carroll conformal algebra in any dimension. D has to be at least 2. And the key observation that was made by Duval, Gibbons, and Horvath more than a decade ago is that the Carroll conformal algebra in D dimensions is isomorphic to the BMS algebra in D+1 dimensions. I will introduce the BMS algebra in more detail in my next lecture later this week. For today, it's enough to know that this BMS algebra generates the asymptotic symmetries of asymptotically flat spacetimes for a standard class of boundary conditions in asymptotically flat spacetime. So it plays the same role as the conformal symmetries in anti-de Sitter space, in particular as the, for instance, the two-dimensional conformal symmetries, the Brown and O symmetries in ADS3. Okay, and if you wonder why there is this relation from a purely geometric perspective, if you look at the metric on Scry, for instance, on Scry Plus, you automatically find it has a Carrollian structure because you pull out this Weil factor, R squared, which is degenerate. I mean, R goes to infinity as we go to the asymptotic boundary. And then you have the metric of the celestial sphere, a minus 1 over R squared du squared. So U is the retarded time. And since R goes to infinity, this factor here goes to 0. So this is the 0 in the Carroll metric. So that's why you get the degenerate signature at Scry. All right. So because of this isomorphism, this suggests that Carrollian symmetries should be important for flat space holography. And a natural conjecture because of this isomorphism is that the dual field theory to asymptotically flat spacetimes, I mean to gravity in asymptotically flat spacetimes, is a Carrollian CFT in one dimension lower. So instead of ADS D+1 CFT-D, we would have flat D+1 CCFT-D correspondence, where by CCFT I mean Carrollian conformal field theory. Okay, so this is the main motivation for me, at least. And it's also the main motivation that I'm going to use in my lectures, why we care about Carroll symmetries. And honestly, if this was the only motivation, it would be sufficient to care about it, because we want to know, does holography work in spacetimes beyond anti-de Sitter space? Does it work in our universe? And does it work in situations where we have a good approximation to say there's an isolated system like a black hole or a bunch of black hole or some isolated galaxy or whatever, and we neglect everything else in the universe. And in those situations, space-time is well approximated by an asymptotically flat space-time. So we want to understand, does holography work in asymptotically flat spacetimes? And since the symmetries match, it's very suggestive to study Carrollian conformal field theories, learn more about them, and see if they can be of any use for flat space holography. Having said this, there's a bunch of additional possible motivations or applications where Carroll symmetries appear. The earliest one that I was able to find, well, I mean, I was able to find it by looking at this review by Elbistan, Zhang, and Horvath, so they were able to find it. Is this paper by Soriot from 73, where he realized that plane gravitational waves naturally have these Carroll symmetries, and they argue that this may be important for memory effects. Another early pioneer of these Carroll symmetries was Mark Yano. He was interested in zero signature spacetimes, in physics very close to the Big Bang or to the initial singularity, BKL physics, Belinsky, Karatnikov, Lifshitz. And well, there's at least a heuristic way how you understand immediately that Carroll symmetries could be important there. When you come very close to singularity, your geodesics are forced into a smaller and smaller light cone in a sense. So you have this ultra-local physics. If you're very close to a singularity, you can no longer communicate with neighboring points very well. And Mark was the first one to realize this connection. But then there are more applications. I will not go through the whole list here in detail. People have tried to apply it in cosmology. I think a main feature is that Carroll symmetries are intrinsic to null hypersurfaces. So whenever you have some null hypersurface naturally appearing, like in the case of black holes, it's very suggestive that Carroll physics should be of relevance. And there is more, but I will not go through these applications here. All right. Now, let's delve a bit more into detail of Carroll symmetries. There's a bit of a zoo of possible Carroll conformal algebras. So which one should you use? Oh, sorry. Is someone asking a question?
Yes, there is a question. I think they put it in a direct message to me, but Kami,
Okay.
if you want to, I can unmute you if you would want to. Just let me find you. Okay.
Hello, can you hear me?
Yes, I can hear you.
Yes.
I was just wondering if there's any like intuitive reason for like whether there's any connection between the physical interpretation of the symmetry as being like the c goes to zero limit, and if there's a connection between that and why it appears as the holographic dual for the flat space holography.
Yeah, in a sense, you see this from this equation here. So this is the metric at scry. We have an I equals constant surface, but we send R, the radial coordinate, to infinity. And you can pose the question, what is the boundary speed of light? So the boundary metric is given by the metric in this parenthesis here. So it's the metric of the celestial sphere, which is, whatever it is, depends on the dimension. But it's a non-degenerate metric. So this is signature, well, plus, 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 plus. But there's also the null time, I mean, retarded or advanced time, depending on whether you're on scry plus or scry minus. And the prefactor in front of this is 1 over r squared. So this 1 over r squared is like the effective speed of light at the boundary surface, which in this case is scry. And as r goes to infinity, this effective speed of light tends to 0. So that's a way you can understand it. It's not that the bulk speed of light goes to 0 or something like that. So we're not doing a limit where we do something weird in the bulk. The bulk is standard Lorentzian physics. But as you approach the boundary metric behaves like a Carrollian metric more and more the bigger the value r, the bigger the value of r is. And if r goes to strictly infinity, then this goes strictly to 0 and you have strictly a Carrollian metric.
Okay, thank you.
Yeah, okay. Okay. Yes, so this is the algebra of the Carroll conformal killing vectors in d spatial dimensions. So it's just going through the exercise of calculating all these Lie brackets. It's not very complicated. Now, the color coding works as follows. So if you know conformal symmetries, then you have seen already all the brackets in black. So I will not go through them in detail. If you don't know anything about conformal symmetries, I suggest you, well, look first at some introductory lectures on conformal symmetries, because otherwise it may be a bit hard to follow what I'm about to say. But the only changes here as compared to standard conformal symmetries are the red commutators, and they involve all super translations. So that makes sense, of course. This is the main new thing as compared to standard conformal symmetries. So first and foremost, they commute mutually, as I mentioned already. That's why they're called super translations. And then with the other generators, they give again a super translation on the right-hand side with some action on this function. So it's, well, not very complicated, but you see, this expression is a bit lengthy. So, okay, you just have to work through this algebra. It's not complicated, but yeah. Okay, so this is the standard plain vanilla Carroll conformal algebra. Now let me mention some generalizations. The first one is a very natural one. You can allow for anisotropic scale invariance with some Lifshitz exponent z. So what I mean by this is you change the dilatation generator in this way. So you have z t dt plus x I di, and z is some arbitrary, in principle, real number, though typically it's some integer. And in the isotropic case, you would have z is equal to 1. And this is, of course, known from generalizations of conformal symmetries as well. But in the Lorentzian context, introducing this is a bit unnatural. And the reason it's unnatural is because once you introduce anisotropy in a Lorentzian context, you automatically break Lorentzian boosts, because Lorentzian boosts don't discriminate between space and time, but this dilatation generator does. However, in the Carrollian context, you already discriminate between space and time from the very beginning, right? Because we have contracted the speed of light to 0, the light cone collapses, time is relative, but space is absolute. So we already have a difference between space and time. And that's why it doesn't do you much harm by allowing for this anisotropy. So it's a straightforward generalization to just allow z not equal to 1. And there are applications where this can be very useful. So I quote here some gravitational context where this generalization turned out to be useful. And there's a corresponding generalization of the BMS algebra. So there's some, arbitrary parameter that you can inject into the BMS algebra, and that can be algebraically and physically useful. Now, another generalization is that you can include superrotations. By which I mean you impose fewer or no restrictions on this yi. Remember that this yj's had to be compatible with the spatial part of the conformal killing vector equation, but you can generalize this if you want. So this was done by Barnich-Trosser, and then even more general by Campilli and Lada. The biggest generalization that doesn't include all the diffeomorphisms would be the so-called Carroll diff algebra. So this would be diffeomorphisms that sort of maintain these different rows of space and time, in the sense that the spatial part of the diffeomorphisms just contains functions that depend on space. So you're not mixing space with time here. But the temporal part can have diffeomorphisms that are arbitrary functions of space and time. So this is the most general thing you could consider. And there are some applications of this Carroll diff algebra. By the way, I should say that while I do give some references, I'm not going to be very complete in providing references. So I will mostly refer to this review by Arjun and others for further references. Okay, so what else can you do? Well, whenever you have space-time symmetries, there's a well-known story. We can gauge the space-time symmetries and in this way get a gravity theory. That's not how Einstein gravity was conceived historically, but you can always have fun with this alternative histories, how science could have developed. So in principle, it would have been possible to start with Poincare symmetries and directly use the Cartan formulation, gauge them, and then you end up with some Einstein-Cartan theory of gravity. And you can do the same with the Carroll symmetry. So if you gauge the finite Carroll algebra, you get Carroll gravity. And this was already done by Yelle more than a decade ago. Okay, then there are more generalizations and extensions, some of which you probably could have guessed. So you can make everything supersymmetric. I will not discuss this here, but it's more or less straightforward. And there are also higher spin extensions, and you can combine both of these generalizations. All right, now instead of generalizing, let me now zoom into one aspect of the finite Carroll algebra, so even without conformal symmetries. So I'll just focus now on translations, boosts, and rotations. And the commutators I want to highlight are the ones in color. And the main commutator that is profoundly different from Lorentzian, but also Galilean ones, is the first one. So the Hamiltonian commutes with Carroll boosts. And well, this is a simple algebraic statement, and you can check for yourself that it's true. But it's physically, at first glance at least, very counterintuitive, because we're so used that when we boost the state, we change its energy, that this is a very surprising statement. So recall that it's even true in Galilean physics, then when you boost the state, you change its energy. And it makes sense. But it's not true in the Carrollian universe. No matter how much you boost, the Hamiltonian doesn't change. And this is responsible for many of the physical features that we associate with specific Carrollian systems, like the flat band structure when the light cone in momentum space opens up and you get a dispersion relation where energy is independent from the momentum, or the soft hair properties of black hole. You can understand it in terms of the Hamiltonian of these soft hair excitations being zero, tensionless strings, etc. So if you take away from all these commutators only one, it should be the one in red. That's really I would say, defining property of any Carrollian system. The second commutator is also different from the Lorentzian case. The Carroll boosts commute with each other, so you don't have any analog of Thomas precession, but it's a bit less unusual because this is also true in the Galilean case. And finally, the last commutator here shows that the subalgebra generated by H, Pi, and Bi, so translations and boosts, is actually a Heisenberg subalgebra of the Carroll algebra. And in this Heisenberg subalgebra, this quantity H appears as a central element. So that's again an unusual property of this algebra. The Hamiltonian is a central element of the algebra. Okay, and as an exercise, if you want to do a simple calculation, simpler than deriving the Carroll conformal killing vectors, you can convince yourself that this Carroll algebra preserves the Carroll structure. So if you act with vector fields H, Bi, Pi, or J, Ij on the Carroll metric and on the Carroll vector field, they're not just conformal killing vectors, but actual killing vectors. All right.
Yeah, we have
Yes.
a question in the
Sure.
chat.
Yes, you can unmute yourself if you want to ask the
Yes,
question.
I will come to unmute.
Yes, I had a question.
Yes.
So, is energy conserved within Carrollian geometries from this commutation? Can we say that?
If energy is conserved, you mean?
Is energy conserved within Carrollian geometries and symmetries?
It may or may not be conserved. Like in other physical systems, that depends what the physical system does. Is it a closed physical system or not? If it's a closed physical system, then there will be energy conservation. But you can have, even in the Carrollian case, situations where the system is open and you have fluxes passing through your boundary. And in that case, there's no reason for energy to be conserved in the same way that there's no reason for energy to be conserved in Lorentzian cases when you have an open system. So this has nothing to do with the system being Carrollian or not. And the fact that this commutator here vanishes doesn't tell you if a given system has a conserved Hamiltonian or not. That depends just on the time dependence of that system and whether it's open or not. Okay. All right. Then I'll move on. So if you know a bit about conformal field theories, then you will remember that there's something special in 1+ functions. CFT2 has infinite symmetries given by two copies of the Virasoro algebra, which I've displayed here. So the L plus minus n are the Virasoro generators, n and m are integers, and plus minus is just because there are two copies of them. the first term would just give you the width algebra with the standard structure constants n minus m. So this gives you diffeomorphisms of the circle. But then there's this famous Virasoro cocycle. So you can have a central extension with central charges given by C plus and C minus. And in a holographic context, the values of the central charges were first calculated in this famous work by Brown and Deneau 40 years ago. And there the central charges are given by 3L over 2G, where G is Newton's constant, and L is the ADS3 radius. And on this slide, I address what happens in the Carrollian limit. So let's take this limit. So you can obtain the Carroll conformal algebra in 1+1 dimension from an Inouye-Wigner contraction of this Virasoro algebra. You first linearly recombine the generators in this way. So the super rotations, if you allow me to call them that way, I label as Ln, and they're given by the difference of the Virasoro generators, where I also put the minus sign in the second index here. And the super translation generators are the sum of these generators, of the Virasoro generators, again with a minus in the second index, but rescaled by a factor 1 over L. And the intention is to send the ADS radius to infinity. So this is a singular limit, a singular contraction of this algebra. And before I write down the precise algebra, you can already see schematically what's going to happen. So L is order 1. So L with L is order 1. So therefore it has to be L times something. L with M is order 1 over L. So the right-hand side has to be M. But M with M is order 1 over L squared. And there's no generator that has a 1 over L squared. So that means if you take the limit L to infinity, this is going to be 0. So this is why you can see already at this stage that these are going to be the super translations. And you have infinitely many of them. Now, if you do what I just said a bit more carefully, it's just a few lines of calculation, then you find this is the result. So this is the Carroll conformal algebra in 1+1 dimensions, including its central extensions. So you can derive this either straightforwardly as a limit, or you take the limit just of the width algebra and then ask the question, what are the most general cocycles that you can add to this algebra? And you would find the same answer. So you have, like in the Virasoro case, two central extensions possible, CL and CM. But unlike in the Virasoro case, they are qualitatively different. In the Virasoro case, C plus and C minus are just parallelity flipped versions of each other, and there's no qualitative difference. Here, there is a qualitative difference. Why? Well, the first line is just the Virasoro subalgebra. So the CL is a usual Virasoro cocycle. But the CM, even though the right-hand side looks like a Virasoro algebra, note that the left-hand side is a mixed commutator between L and M. So that's why this is qualitatively different. And if you check what happens in a holographic context, plain vanilla holographic context where we have Einstein gravity and no gravitational anomaly, then C plus is equal to C minus, and CL is always given by the difference of the parent central charges. So that means CL is actually 0 in a holographic context. But CM, curiously enough, at first glance, you might think it's going to be 0 because it's C plus plus C minus divided by L, and L goes to infinity. However, note that C plus and C minus scale linearly in L. So these factors L cancel, and you just get 3 over G. So you get something that is non-zero. And weirdly enough, it's dimensionful. So since this often leads to confusion, let me point out that the precise value of the CM doesn't play a role. However, it's still important whether it's 0 or non-zero. And what does play a role is the ratio of CM to other quantities of the same dimension, for instance, to M naught eigenvalues of a certain state. And if you do some change of basis where you rescale M by an arbitrary constant, you see that M appears linearly, and here it doesn't appear at all. So that's an allowed change of basis. But if you do this, you would change the value of CM to some arbitrary other value. But at the same time, you would change also M naught eigenvalues. You would rescale them in the same way. So there's still some intrinsic meaning to dimensionless ratios constructed with CM. And there's still a way in which you can say that CM is small or large as compared to other quantities of the same dimension. Okay. And well, geometrically, the Ln generates super rotations or diff S1 and the Mn super translations. So in the remainder of my lecture, I will now focus on Carrollian conformal field theories with arbitrary values of CL and CM. So I'm not necessarily restricting myself to this limit of Brown and O. I'm allowing more general situations. From a holographic perspective, for instance, because you may want to discuss also topological massive gravity or other gravity theories where you have a gravitational anomaly and CL is non-zero, or because we're just intrinsically interested in Carrollian CFTs without any holographic motivation. Okay, so on the next slides, I give you some of these details, and I zoom in onto some more technical aspects of Carrollian CFTs in 2 dimensions. Now, the first thing that I'm going to discuss is states and representations. So you can label states by the eigenvalues of L naught and M naught. I denote them by delta and psi respectively. And that those eigenvalues, delta and psi, play a similar role to the conformal weights that you're familiar with from conformal field theories. So H left and H right, or H plus and H minus, or delta plus, delta minus. They're different notations, but there are always 2 conformal weights, and the same is true in the Carroll conformal case in 2 dimensions. Now, a natural looking representation is the highest weight representation, and that allows you to define primary states. So primary states are defined by the conditions that they are annihilated by Ln and Mn for any positive integer n. And such states are called CCFT primary states, and I label them, well, by the subscript P for primary. Generic states are then descendants of these primary states. That's again, in analogy, how you can produce primary states in the Virasoro case and descendants thereof. So these are generic states, and you act with the raising operators, which are just the L minus n's and L and M minus m's with positive integers n and m. So the negative indexed BMS generators or Carrollian CFT generators, they act as raising operators, and the positive indexed ones as lowering operators, just like in the Virasoro case. However, let me point out that besides this very natural looking representation, there's another one that can be natural in other contexts. So this highest weight representation is natural if your approach to Carroll physics is an intrinsically Carrollian. If you don't have any parent CFT or some gravitational context, then I would argue this is a very natural representation to use. But there's another one that is important, and this is the so-called induced representation. And the associated induced, I guess, primaries, you could call them. I denote them by a subscript I for induced. And they're defined by the condition that the supertranslation generators for any non-zero n annihilate such states. So notice that n can have any sign. So this is true for positive n and for negative n. And there's no condition on the else. So these primaries are very different from the standardized weight primaries. And descendants thereof, well, then they are generated by acting with arbitrary superrotation or Virasoro generators on these states. And again, there's no constraint on the sign of the n here. So why do we care about such induced representations? Well, it turns out they're very natural if you approach a Carrollian CFT as a limit from a relativistic one. I'm not going to show this in detail, but it's not a difficult calculation. And if you're new to this but want to learn more, I encourage you to do this calculation. It takes you less than half a page, I guess. You can show that these induced primaries descend from standard CFT highest weight primaries. And these induced representations therefore descend from the standard CFT2 highest weight representations. So if your goal is to start with a relativistic CFT and have usual states, meaning highest weight states, and you ask the question, what happens if you take the Carroll limit? The answer is you're going to get the induced representations, not the highest weight representations. There's also a way to get the highest weight representations as a limit. That requires the so-called flipped representations on the CFT side, where you use highest weight in one sector, lowest weight in the other sector. But I will not show this in my lectures here. I'll give you a reference at the end where you can find this in more detail. So this explains why both of these representations have appeared in the literature, because both have their role to play. The highest weight ones are useful for intrinsic discussions. The induced ones are useful in many contexts where you approach your Carroll CFT as a limit from a relativistic one. Okay, so next topic I want to discuss are correlation functions. Now, in standard conformal field theories, you know that the conformal symmetries are strong enough to determine the 2- and 3-point functions up to some normalization coefficients. And the same is true in the Carrollian case. So let me show you how this works. So this is again the Carroll conformal algebra, the infinite dimensional one. And there's a subalgebra of this that is blind to the central charges. So this is just generated by these finitely many generators, L naught, L plus minus 1, M naught, M plus minus 1. So this is like the SL2R plus SL2R invariant subalgebra of the Virasoro algebra. And that generates the global Carroll conformal field theory symmetries. And the 2 and 3 point functions are constrained by those. The geometric interpretation of these 6 generators is as follows. So the L-1 and M-1, they generate translations. The M0 generates Carroll boosts. The L0 generates dilatations. And the L1 and M1, they generate special conformal transformations, the temporal and the spatial ones. And now we're going to use them to constrain 2-point functions. So here's schematically how this works. We consider some arbitrary 2-point function between primaries with some weights xi12 and delta12. O1 and O2 are some arbitrary operators. And this is how I denote the 2-point function. Now,
Daniel?
yes.
Sorry, yeah, there's a question.
Sure.
I think it was for the weights that you mentioned before. I guess the highest weights, they are asking the weights are integers.
They don't have to be, but they don't have to be. Typically, they are rational. But well, there are also many instances where they are integer. But they don't have to be integer. Typically, they are rational. I'm not sure if there are good applications where there are arbitrary irrational numbers. It's a bit like in CFT, the weights don't have to be integers. You can have, for instance, in the Ising model, you can have weights like 1/2 or something like that. But they're typically irrational numbers. Okay. So yeah, so 2-point function, yeah. So the translation invariance just means the 2-point function can only depend on the difference of the arguments. That's exactly the same derivation as in the relativistic case. The Carroll boost invariance, well, leads to a slightly different constraint from the relativistic case. So that means that this arbitrary function of space and time splits into an arbitrary function of space that is at the moment not further determined. And then this exponential that depends on this cross ratio between the time interval difference and the spatial interval difference. And here there has to appear the sum of the weights, the sum of the supertranslation weights. Dilatation invariance, like in a relativistic CFT, constrains this function to be monomial. So it has to be some arbitrary normalization constant that we cannot fix, divided by the difference x1 minus x2 to the power delta1 plus delta2. So this is very similar to the relativistic case. And the invariance under special conformal transformations requires that these weights are actually equal to each other. So xi1 has to be equal to xi2. So I just dropped the index. And similarly, delta1 has to be equal to delta2. So the upshot is that the 2-point function is given by this simple expression. And this is reminiscent of what you get in relativistic CFTs. Moreover, the CCFT weights have to match for this to be non-zero. Now, okay, I wrote n 3-point functions, but I'm not going to display the 3-point functions. But 3-point functions, there's a similar story, and they're again determined by some normalization constants and otherwise contain monomial factors in differences between the insertion points of the operators. Okay, so I guess I have about 5 more minutes. Is that right?
Yeah, you can take. I mean, we have until 11:30, so
okay. I don't want to take that long, but
much.
no, I will not rush it. I don't have so many slides anyway, so I just proceed in normal speed. Okay.
Yeah.
Yeah. So next item is the Carroll conformal field theory stress tensor. So this is analogous to the Virasoro stress tensor. I'm now in the cylinder with coordinates tau and sigma. So sigma is 2 pi periodic and tau is the Carrollian time. And recall that the Virasoro stress tensor is composed of the Virasoro modes. So you have an infinite sum over all integers, ln, and then you have e to the minus I n sigma and the shift by the central charge. And in the Carrollian CFT case, the construction is similar. So there's a super translation version or super translation component of the stress tensor, m of sigma, which is given by all the super translation modes, weighted by this Fourier factor e to the minus I n sigma, and then shifted for convenience by the vacuum gap, so plus Cm over 24. And then there's an additional term, additional component to the stress tensor. And unlike in a relativistic CFT, the situation is not symmetric. In the relativistic CFT, again, there would be a left moving part of the stress tensor and a right moving part. And the only difference between them is that instead of plus indices, you have minus indices. But here there's a slightly bigger change. So there's this super rotation part of the stress tensor, and that consists of both the super rotation generators and the linear term in tau times the super translation generators, again weighted with this Fourier factor and shifted by the vacuum gap CL over 24 whenever this is non-zero. And you can show, I will not show this here, but you can show that the two-point functions of the cylinder take the following form. So let's start below. The super translation part, that just gives 0. And that remains true for any higher point insertion. So whenever you have 2 or more insertions of this super translation part of the stress tensor, the corresponding correlation function gives 0. If you have one super translation and one super rotation insertion, the right-hand side looks precisely like in a relativistic CFT on the cylinder. So you can obtain this result in the relativistic case just by the usual exponential map between the plane and the cylinder. And then the well-known factor, central charge divided by 2 times z to the 4 gets transformed into this sine to the 4 expression on the cylinder. And the same happens here. So you get the sine to the 4 sigma 1 minus sigma 2 over 2. Even the factor matches. And you get this mixed central charge, the BMS central charge, as I like to call them. So the central charge that is in the mixed commutator. And the super rotation two-point function looks a bit more complicated. So the CL part is like in the Virasoro case. And indeed, if Cm is equal to 0, you get a Virasoro subalgebra, and this is the right two-point function. But if Cm is non-zero, you get also this additional term that is linear in the time interval difference and has this additional decoration with a cotangents function. So even though the structure is somewhat similar, there are some important technical differences to the relativistic case. Moreover, there's an analog of the conformal word identities in the Carrollian case. So for Virasoro, the conformal word identities are just the holomorphic and antiholomorphic flux conservation laws. So in standard notation, I guess dc bar of tzz is equal to 0. So the fact that the stress tensor flux component has to be holomorphic or anti-holomorphic. And the Carroll conformal word identities are a bit different. So if you have an arbitrary operator and you insert it in a 2 or n-point function with the super translation part of the stress tensor, then the statement of the Carroll conformal word identity is that the tau derivative of this has to be 0. Well, okay, this is sort of obvious because m depends just on sigma. And the second word identity relates the tau derivative of n in such an insertion with the sigma derivative of m. So this is because if you take the tau derivative of this expression here, you get a minus INM, and minus IN is also what you get when you act with the sigma derivative on the left, on the super translation part of the stress tensor. And you can use this if you insert for O either m or n, you get constraints on the two-point functions. And if you insert for O 2 insertions, so like 2 n's, for instance, then you get constraints on the 3-point functions, and you can use this to recursively get all the n-point functions of the Carroll conformal field theory stress tensor. So even though higher n-point functions like 4-point functions, 5-point functions, and so on are not uniquely determined by the symmetries, but involve some analog of the conformal cross ratios, the endpoint functions of the stress tensor, they are all determined once you know the central charges. That's true both in the CFT and in the Carroll CFT, and this is the complete induction way how you can derive them. I will not show this in detail here, but I'm just telling you how you can do it. Okay, so this is all I want to say about the stress tensor. Let me now give you an outlook on Carroll conformal symmetries. So yeah, I think I'm good in time. We have just 1 hour behind us, and this is actually the last slide. Here are some relevant symmetry-related topics that I will not discuss in detail, but I still want to mention them to give you a chance to either ask questions about them or to give you some hints to the literature. You can find more about these details. So the first concerns Carroll conformal characters. In the Virasoro case, it can be very useful to express, for instance, partition functions or other observables in terms of characters of the Virasoro algebra. And you can do something similar in the Carrollian case. Here I'm just displaying the Carroll conformal characters without explaining how to obtain them. So this is the generic highest weight character, chi. It depends on the value of the central charges and on the Carroll conformal weights, psi and delta. And moreover, on your chemical potentials, rho and sigma. Now, the quantity on the right-hand side, besides these oscillating terms, contains the Dedekind eta function with sigma as an argument. So here's again the definition of the Dedekind eta function. The same eta function appears also in Virasoro characters. And this is well defined for sigma in the upper complex half plane. Of special interest is the vacuum character. So when psi and delta vanish, I denote this by chi 1. And okay, then you get some simplifications here. All right, so these are Carroll conformal characters. There are also Carroll modular transformations. So if you consider Carroll CFTs on the cylinder, you have modular transformations like in the relativistic case. And they act on your chemical potentials or modular parameters in a slightly different way from the relativistic case. So the first transformation here of sigma is just like in the Lorentzian case. So sigma goes to a sigma plus b over c sigma plus d, where a, b, c, d are integers subject to the unit determinant constraint ad minus bc is equal to 1. So if you're familiar with modular transformations in the relativistic case, then you will recognize that this is exactly the same transformation behavior. But this other parameter, this other modular parameter rho, transforms in a different way. It transforms more like a modular vector, so it transforms into rho over c sigma plus d squared. Moreover, you can show that the generic modular transformation generated here can be composed of basic building blocks, namely of so-called S and T transformations. And that's, again, completely analogous to the Lorentzian case. So also there you can compose general modular transformations out of S and T transformations. S transformation is like a duality. Physical interpretation is often as a low-high temperature duality. In this case, what it does is it sends sigma into minus 1 over sigma and rho to rho over sigma squared. And the T transformation is just a shift of sigma. That's exactly the same as in the relativistic case. So the T transformation just sends sigma to sigma plus 1 and rho to itself. And I'll leave it to you as an exercise to show that these building blocks obey the usual braiding relations that also the standard modular transformation in the relativistic case obey, namely S squared is 1. So if you apply this S transformation twice, you get back the identity, and ST cubed is equal to 1. So the first one you can probably see by inspection. The second one you have to do like 3 lines of calculation, but it's not hard. And why are these Carroll modular transformations useful? Well, they allow you to derive something like the Carroll-Cardy formula. I'll not give you the derivation here, I'll just give you the final result. So this is the entropy of some state in a certain regime of a Carroll conformal field theory. And that state has certain expectation value of the super translation eigenvalue psi and the super rotation eigenvalue delta. I rescaled psi by this factor 24 over cm to make this quantity dimensionless. And the result is a term that is similar to the usual Cardy formula, 2 pi Cl over 24 squared of psi tilde. So this is like a Carrel version of the Cardy formula. But then you have a second term that is not familiar from the standard Cardi formula, and that's given by 2 pi delta tilde over square root of psi tilde. So you have a recurring theme here. There are conceptual similarities to relativistic CFTs and even some technical similarities. Certain terms, like the first term here, are identical to what happens in the relativistic case. But then there are other terms that look completely different from the relativistic case. You can also do Carroll conformal bootstrap. Let me gloss over this and refer you to this review by Arjun and friends from half a year ago. So, for instance, the 4-point conformal block you can construct conceptually in a similar way to relativistic CFTs using crossing symmetries. And this 4-point function here is given by the OPE coefficients associated with 3-point functions and this conformal block that you can calculate. I also want to make some remarks on Carroll partition functions. So Carroll partition functions are one of the main reasons why it's useful to work with these Carroll conformal characters, because you can express a Carrollian partition function in the grand canonical ensemble. So rho and sigma are chemical potentials, which you can interpret as modular parameters. And you can express this partition function as a sum over all the allowed Carroll conformal weights, xi and delta of your primaries in your system. Then you have some degeneracy or multiplicity of your primaries with weights xi and delta. And then you have the corresponding Carroll conformal character. So that's a very neat and useful way to express a partition function. The same is, of course, true in the relativistic case. The only difference here is that these chi's are now not Virasoro conformal characters, but Carroll conformal characters. I also want to point out one subtlety with chemical potentials. If your goal in life is to obtain Carroll conformal field theories as limits from relativistic ones, there's always a subtlety you have to deal with, and it's contained in this second equation. So the angular rotation chemical potential, there's no subtlety. It takes the same value in the parent CFT and in the Carrollian CFT. It's this quantity I called sigma up to some factor 2 pi. But the inverse temperature, which is related to the quantity I called rho, that gets singularly rescaled. So this parameter epsilon is essentially the Union-Wigner contraction parameter, and it goes to 0. So if you insist that your inverse temperature in your original CFT remains finite as you approach your Carroll limit, that means your inverse temperature in the Carroll limit has to blow up. It has to go to infinity. There's no way around this. So that means you're forced to temperature to a singular value of the temperature. On the other hand, if you want to have a finite result for the Carroll temperature, inverse temperature, that means as you approach the Carroll limit, you have to scale your inverse temperature in the CFT side correspondingly. So you have to compensate this factor epsilon over there. This is not an issue if you work intrinsically in a Carrollian CFT, but it would be an issue if you approach it as a limit. So you have to be a bit careful how you take the limit. And if you don't take care of this rescaling by epsilon, you may end up with, some result that tells you the partition function doesn't exist or is singular. And this may not be true if you do a proper rescaling of your temperature in the CFT. Okay, I think this is the last point. So there is a feature known as vacuum dominance that appears already in the Lorentzian case, so in Lorentzian CFTs. What it means is that the S-dual partition function is dominated by the vacuum character. So if I may go back a little bit. Sorry, where was the partition function? Here. So the partition function is a sum over primaries, and that can be very complicated. But there are certain limits where this whole sum is dominated by a single term. And if that's the case, well, your partition function obviously simplifies. You have to take into account only one character. And if that single primary that dominates your partition function is the vacuum primary, well, things get even simpler because the vacuum primary has very simple properties. So in that case, all you need to do is to calculate this prefactor here, and then you're done. So whenever you have this vacuum dominance, well, that's, of course, a very useful property because it allows you to calculate for instance, things like this Cardi formula. That's a consequence of such a vacuum dominance. So that's one of the applications of vacuum dominance. And it turns out that in the Carrollian CFT case in 1+1 dimensions, the S-dual partition function, so after you do this S transformation, is dominated by the vacuum character in 3 distinct cases. There's the Cardi case. In this case, the angular rotation parameter has to be negative and the temperature has to go to -infinity. So this is something you need to digest. The temperature not only has to be large, it has to be large and negative. I'll give you some holographic interpretation of this weird sign of the temperature. It's going to be a recurring theme also in the next lecture. And I'll explain where it comes from on the gravity side. But it's unusual, but it's not something that is forbidden. You can have negative temperature, and temperature going to -infinity, well, it's as negative as it gets. And it's in this regime that you recover the Cardi formula. Now, it turns out that there are 2 other regimes. The second one, that was our main interest in this paper by Ankit Agarwal and collaborators, which came out just recently ago. That's one of the few papers I mentioned here, well, partly because it's of relevance for this point here, but also because I wanted to highlight Ankit's involvement, who has been quarterbacking this work and who is currently searching for postdoc positions. And since now is sort of the crucial time, I wanted to mention his name explicitly. In any case, so the Schwarzen sector is in some sense the opposite of the Cardi sector because the temperature goes to 0. But again, it goes to 0 from a weird sign, namely it goes to 0 from below. So it has to be slightly negative as it approaches 0. And also omega goes to 0 from below. And then there's a third sector, which we call Boltzmann sector because it's the only sector where the temperature is actually positive, like for any decent Boltzmann ensemble. So in that case, the temperature is positive, but the angular potential has to take a weird limit. It has to go to I times 0. In the previous cases, the angular potential was real and temperature as well. Here, temperature is also real, but the angular potential has to be purely imaginary. Now, yeah, there's a very detailed discussion of this in this paper here. I'll not dwell further on this, but just wrap up. So what are the main takeaway lessons from my first lecture? If you only want to remember slogans, well, here are the 4 slogans that I suggest you remember. The first one is the Carroll symmetries are formally the C to 0 limit of Poincare. That's just a fact. Second, the Carroll symmetries, the Carroll conformal symmetries are infinite dimensional because the appearance of supertranslations. That's also just a fact. The third one is that the Carroll conformal algebra in D dimensions is isomorphic to the BMS algebra in D+1 dimensions. I've made the statement. I've not shown you explicitly this algebra. I will do so next lecture. So this is definitely a fact. And the conjectural part of this fact is that this is therefore of prime importance for flat space holography because the BMS symmetries are of relevance for flat space holography. I will belabor this point quite a bit in the next 2 lectures. And last but not least, what I try to show in the second half of my talk is that in the particular case of 1+1 dimensional Carroll conformal field theories, there are lots of conceptual similarities to CFT2. You have characters, highest rate representations, modular transformations, a Cardi formula, bootstrap, partition function in terms of characters, vacuum dominance. But there are also many technical differences. So you cannot just naively take over what you know from relativistic CFTs. There's a bit of work you have to do, and some of the work you might obtain as a limit, but more often than not, it's easier to work intrinsically and not rely on limits because the limit is always singular, and you may have a hard time figuring out how to rescale your observables to get the right Carroll limit. Okay, I think that's a good place for me to stop and take a question because otherwise I would already be starting with my second lecture. Thanks.
Thank you, Daniel. I will stop the recording now and then we can proceed to the session.
Okay, sure.